SLAM is nothing but simultaneous localization and mapping algorithm. Let's just have a quick chat in terms of what area are we trying to cover here. In today's world, we have a lot of autonomous systems that are coming into play. Systems that are being developed for autonomous vehicles or autonomous robots or any such autonomous applications are very vital and pretty fast rate in today's world. One of those systems that we are talking here about today is SLAM, which is nothing but simultaneous localization and mapping, which is one of the primary components of these autonomous systems. So let's go ahead and start with it. Simultaneous localization and mapping. For example, let us think about ourselves. What do we need to know, and what do we need for us to understand where we are at and how we see ourselves to be at any given location? We need to know the surrounding, and we also need to know where exactly we are in that surrounding. That is exactly what is being done for a robot using the SLAM systems. If you look at the state estimation and the corrective action, what does those mean? State estimation is defining what state you are in, or it will define where exactly you are supposed to be in, and where are you at currently. So that is defined by the state of the system. And corrective action is nothing but the action that is taken based on the algorithm that you have, the SLAM algorithm that you have, to correct the system's action and put it in the right pose as you intend it to be. This is where, so here is where the algorithm comes into play, right? The corrective action and also making the robot aware of its current position is where the SLAM algorithms come in. So let us go into the next part of it. So here is an example that I'm taking where you have a robot in a given environment and you have different components of the environment. Let's say they're environment occupants. So what are environment occupants? For example, let us take an example of autonomous vehicle. You have an autonomous vehicle. You have different other cars on the road as well along with you. That is one of the environment occupant. And you have the traffic lights that a car is trying to read. That is an environment occupant. So all of these different components that are comprised within the environment are termed as environment occupants. So how does the robot perceive itself when it is in a given environment? It needs some kind of an information, right? So before we go there, let us talk about the robot pose. What is a robot pose? How do we define it? A robot pose is nothing but it is a characteristic of the robot that will give you the position and the heading of the robot, which means that for any robot, if you take any example, whether it's a humanoid robot, whether it's an autonomous vehicle, whether it's an undersea robot, whatever it might be, two of the major components that you can always rely upon to tell the system that it is at a given location is your heading and distance with respect to the environment occupants, the other environment occupants. I'll go into detail in that regard in the next slide or so, but this is a brief introduction of what a robot pose is. Now coming to reading the environment. How can you read an environment? You need to have some kind of a way to perceive the environment, right? So that's where the sensors come into play. So you have different types of sensors that you have access to today that can read the environment in different ways. For example, a few examples have been given below, which are camera, radar, GPS, and LiDAR. Each of these different sensors give you a certain perception of the environment, which will help you localize and also map the environment that is around you. Each of these can be used for a different function, and also you also have something called sensor fusion, which will help you to use the signals, use the data that is coming in from all these different sensors, in a collective way to perceive the environment and localize yourself or localize the robot in the environment. Let's move on to the next one. Now you understand. Now with the introduction of what you're trying to do here with respect to the SLAM algorithm, let us understand what is SLAM first, right? So for what we've talked about is what are the systems that we are dealing with. We're dealing with robotic systems that need to be localized and also map the environment. So you can say, or you can basically create a way for the robot to, let it know where it is located in the given environment. That is the basic functionality of any given system, whether it's a living being or whether it's a autonomous vehicle, whatever may be the system. This is one of the major functionality that we always look to. So let's talk about SLAM systems. SLAM is nothing but simultaneous localization mapping, as I've talked about already. So there is, as the name suggests, there is two major components in a SLAM system. One, localization, and two is a mapping. What is localization? So let's talk about localization. Localization is nothing but put yourself on the given map, say where exactly you are at. So localization is a function that will tell the robot exactly where it is located at on a given map. When I say map, on a given environment. So environment is defined by the map, right? So for example, let's talk about Google Maps. I think you already, you do use it on a very regular basis, right? So what does Google Maps do? It will put you on a certain location based on different sensor input, right? One of which is a GPS sensor. Like we talked about earlier, you're perceiving the system, or you're perceiving the input, or you're perceiving the environment to the robot to tell you exactly where you are based on certain sensor information. The sensor information in case of Google Maps is coming from a GPS sensor, right? Localization, GPS information helps put yourself on the map so that the robot can perceive as to where exactly it is located on the given map, right? Google Maps is like a really huge map. It's pretty big, right? But how about a system? So take an example of an indoor system like your home, right? In that case, you don't really have Google Maps, right? So you need to be able to first map the system or map the environment. Number two, localize object or the robot that you're trying to localize in that environment. Here is the example, or here is the generic system architecture as to how the system is designed when it comes to SLAM systems. Okay. So first, for any robot, it has to have some kind of a way to perceive the environment. So that is what is the sensor input represents. So it can be any type of sensor, right? A few examples that I've given earlier will give you a brief idea of what types of sensors that we use on a regular basis. But let's not go into details of the sensor types, but let's just stick to the system architecture that we're talking about here. So you have a sensor input. It can be a GPS sensor, it can be a vision sensor, it can be anything. It depends upon the function that you're trying to write and what kind of environment you're in. Now you have the sensor information, right? So you need to perceive the system, or you need to perceive the environment, and then this perceived information is sent into the localization/mapping function. What happens in localization and mapping function? Your system reads the data and it will estimate exactly as to what the environment looks like in its own terms, right? So there is a number of ways to perceive the environment, and we'll not go into a detail about that at this point. But so there are a number of ways to perceive the environment. And now once you have the environment, and you have the sensor information that is coming in as to a tentative sensor information that is coming in as to where you're possibly located in the given map, or that is being read by the robot, and that's where the localization function comes in. You will start to use this sensor information, and you'll start to do some localization algorithm will basically take care of putting yourself or estimating your position as much accurate to the maximum accuracy that it can go to. That is the main that is the main function of localization. And so what happens in a SLAM algorithm is nothing but it will perceive the environment based on the sensor, and it will localize yourself onto the map based on that same sensor information. And how it is done, there is a number of ways to do the localization and mapping function, but we'll talk about it in a very brief way in the next upcoming slides. So I hope you understand what a generic system, and then going after you have the localization and mapping done, the next step is to plan the path, right? For any given robot, you have a source location and a destination location. So you are trying to go to a certain location based on the map, and you have the localized location of your robot based on the map and also the sensor input data. Now you're trying to plan a path in that, you're trying to plan a path from the source to the destination. Okay. Let me show you an example. For example, let's say the robot, wherever it is in the first pose, in the first pose, the robot is the source, is at its source. Okay. In the last pose, the robot is at its destination pose. Now, what are we trying to do with the SLAM algorithm is we are basically trying to plan a path for the robot to go from the source to the destination point based on the sensor information that you have available to you. Okay, so that is exactly what is happening here in a flowchart perspective, wherein you're getting a sensor input, you're perceiving the system, and you're perceiving the environment around you. You're performing you're performing a function which is nothing but a SLAM algorithm does to localize and map the system and the environment, and then plan a path for the system to go from a source to a destination, and then you generate control commands that will basically help the robot navigate in the environment. Okay, so that's a very generic, high-level introduction to what a SLAM is. Now moving on to the next part of this. Okay. As I was saying earlier, a typical SLAM system is the operational principle is shown as below. So again, I'm going to repeat the same statements that I made earlier, but hopefully this will make it more clear if it is not earlier. Okay, step one, you take the sensor input from the sensor surrounding environment. Step two, the sensor input is used to localize and map the environment around you, and this will enable the system to perceive itself as to where it is on the, or it will give a let me put it this way, the sensor input will give an information as to possibly where can the robot be in the given environment, and it will simultaneously construct a map of their environment around the robot. Okay, so now you have the map that is constructed around yourself and the localization function that is trying to estimate the best possible position of the robot, and that function is done by the SLAM algorithm. Okay, so as you can see, this is a simplified, the bottom picture, the bottom flow chart is a simplified version of localization and mapping algorithm. So basically you have a sensor input, you're taking it into localization and mapping functions. It can be one function, it can be two functions. There is a lot of ways to design it. And you're using the sensor information to localize and map the environment, localize the system and map the environment, and then estimate the pose of the system based on these two inputs, or the output coming from the localization and mapping functions. Okay, let's talk about how the SLAM functions are classified as it is today. There's two ways that you can classify a SLAM problem. One is online and one is offline SLAM. Online systems are basically real-time. They work in real-time environment wherein your sensors are reading the environment and also localizing the vehicle or the robot that you're trying to localize onto the map simultaneously, which means that your system is reading the environment and processing the data to localize itself onto that map of the environment in a simultaneous fashion. Okay. The second classification of this is going to be offline SLAM. Offline SLAM is nothing but it collects the data of the environment in before, and then the map, and then creates a map for it, and this map is used to localize a robot. Let's in a different way, or after the map has been constructed, using this previously collected map information from the sensor data. Okay. Going to the next one. Okay. Here are some of the examples, or here are some of the methods that are currently in use for different SLAM systems. Okay. A SLAM. Okay. For any, let's talk about generic system. Okay. You have many different methods of, like, you can have a number. You can have a number of methods of doing or realizing a certain function, right? So what are the different methods of realizing an algorithm? So here are three examples. There are many more methods that are used on a regular basis, but here are a few good examples as to the methods that are used in this in resolving the SLAM problem. Okay, the first one is a Kalman filter. What is a Kalman filter? Here I'll give you a very high-level introduction. We can go into details once we have started up with the course. But here we'll talk about these different methods in a very brief fashion. That way, you get a flavor of what kind of how are you approaching the problem and how are you solving it, right? So this is SLAM problem is nothing but it's a mathematical problem, right? So you're trying to solve a mathematical problem wherein you have, so let me put it this way. You have the sensor information, right? So how do you, so mathematics is called the universal language, because in this case, you're trying to read the environment, right? How do you read the environment? Based on certain measurements, which is nothing but it is converting into some kind of where something that will involve some level of mathematics to it. So these different methods of solving a SLAM problem, they will help us perceive this mathematical problem and solve it, right? So that is exactly what is happening here. Let me talk about these different functions in a very brief way, and then we'll go ahead and talk about some more advanced functions as well in the next couple of slides. So Kalman filter. Okay, I'm going to give you a very brief introduction of these. So bear with me here for a second. So Kalman filter is nothing but a linear quadratic estimation methods that uses a series of measurements and distances from the environment, and produces the estimate of the unknown variables that can be estimated more accurately while using multivariable data. Okay, this might all seem to be a little bit new to all of you, but let me help you understand this. Okay, so let's say you have a robot, right? So you have a robot. So what are you trying to perceive for the robot? One, distance from any given environment occupant, right? That is one. And then position of that or heading with respect to that particular object, or orientation of the object versus with respect to the robot, or the robot with respect to the object, right? All of these come down to certain mathematical numbers, one of which is going to be distance and one of which is going to be heading. You can, let's say we're talking about the green dot that is shown in the bottom picture in the middle. So what is it trying to do? It is trying to take measurements, right? It's trying to take measurements, and it is trying to map the environment as well as estimate its position based on the information that it has available. So the information that it has available is represented by the blue lines down there. What does those blue lines represent? One, distance. Two, heading with respect to heading of the object that the robot is perceiving with respect to the robot, right? So these two information will be the sensor information that the robot is taking in, right? So in this case, because we're talking about the Kalman filter, let's take that example, and you're trying to apply a Kalman filter on the given on the picture below, and the green dot is your robot, and you have the surroundings around you. So you are trying to produce estimates for the unknown variables. What are your unknown variables? Your unknown variables are going to be your position and your unknown variables are going to be your position and the heading of the object or the robot, right? So now we know what we need from the robot, right? What you need is your position and your heading of the robot. Now, what do we know is whatever is the sensor input that you're getting from the environment. What do we need to what do we need to do? So if you might have had a background with control systems, you would understand that any given system or any given object in the environment, in any environment, can be perceived as a mathematical model. Okay, a mathematical model is nothing but it represents the system state, which means that any given system can be represented in in a mathematical model, and this mathematical model can be estimated based on the sensor readings and all the other inputs that can be used to generate the mathematical model for this. So you have the sensor reading, and then you have certain estimate of the certain model that you're trying to generate for the system, right? So there is a predefined. So generally, what happens is you have a predefined structure for the system, the way it should be modeled, and then you try to estimate the different variables that you have in that system based on the information that you're getting from the sensors, and then you try to tune it as you go. That way, you get the correct mathematical model that represents that system. Okay, let's take an example: helicopter. If you are in from an aerospace background, you might know this. You might perceive this better. So this is a very generic example. So I'm going to take that example to explain this. Attributes of the system that will define it. Pitch roll yaw will define the orientation of the vehicle, and then the vehicle velocity, along with this pitch roll yaw and all these different system variables, will define as to where the vehicle is and where it is going to, and all of these different factors. So now, in order for you to do this, you need to have certain measurements taken from the environment. You're taking it from different sensors. It can be GPS, it can be a camera sensor, it can be whatever it may be. So you have the input for the system, or you have the input for the system to be a sensor input, and then you have a certain system which is the structure of which is predefined to some, and you start with it, and then you have the sensor input, and then you try to use the sensor input to reduce the errors and the noise factor that is coming from the environmental factors, and estimate the system mathematical model and try to correct it over time. So that is exactly what happens in Kalman filter. Okay, so you're basing your estimate of the system or on a given mathematical model, and you're trying to get the best out of what you can to represent the system in the environment. Hopefully that's clear. Moving on to the particle filter. Particle filter is nothing but it's a probabilistic problem. When you start the robot in a given environment, then it will think that it is all over the place. It can be anywhere within the entire room. right? Now, what happens is as you go around, as the robot moves around the environment, start to map the environment, and it will start to generate the probability of it being at a given location. As you move around and as the calculations regarding the probability of a given position based on the sensor input are going on in the background, you would see that the probability will slowly come down to, very confined certain location. It is not perfect, but it is as accurate as you can get, with the sensor input that you have. So it depends upon a lot of factors as to how accurate can you get with the system. But probabilistic method wherein you perceive the environment and then you read the environment and you generate the probabilistic position of the robot based on this sensor input. That basically defines higher level of particle filter. Now coming to the graph-based method, can be an example of, before I go to the graph-based method, we were talking about the online and offline SLAM methods. So Kalman filter and particle filter can be considered as one of the two of the online methods, wherein you are doing the mapping and localization simultaneously. And these are two different methods that you can do that. Okay. Now, graph method. Graph method can be considered as an offline SLAM method, right? What is an offline SLAM method? Like we discussed earlier, you have you generate a map based on the sensor input, and you use that to at a later state to localize yourself onto the map. That's what is happening here. So your graph network will represent the environment on the map which are predefined, and your robot will localize to this map on the graph network to show exactly where you are at, and your location, and of course all the other characteristics of the robot. Okay, so now going on to the next one. Here I'm going to just play this video. Just have a look at it. This is a very familiar example as to where the SLAM robotics or the SLAM methods are used in a very extensive way. I'll leave you to listen to this for a second here.
The robot automatically self-adjusts to different floor surfaces as it moves through your home. Roomba's patented 3-stage cleaning system provides comprehensive cleaning coverage. First, the spinning side brush cleans along wall edges. Next, 2 counter-rotating brushes scoop up dirt, hair, and debris. Finally, a powerful vacuum pulls it all into the bin, where the filter traps dust and other fine particles. Roomba cleans under the bed and other hard-to-reach areas. Unlike an old-fashioned upright vacuum, Roomba cleans in tight spots and under and around furniture. But Roomba uses wall-following technology to clean along walls and baseboards and ensure the whole floor is completely clean. Roomba maximizes cleaning by adapting to your unique household environment. Roomba's eye-adapt responsive cleaning technology monitors the environment more than 60 times per second, using multiple sensors and dozens of behaviors to clean your home. Roomba's soft touch bumper provides a cushion between the robot and the objects it touches while cleaning, protecting your walls, furniture, and other household items from scratches and marks. Roomba's 2 HEPA filters capture fine dust particles, minimizing dust recirculation. The robot's Aerovac 2 bin picks up and holds large quantities of hair, limbs, and other debris, so it doesn't need to be emptied frequently. With advanced dirt detection, Roomba uses optical and acoustic sensors to find dirt and debris, intensely cleaning the areas of the floor that need it most. The robot's persistent patch cleaning technology uses a repeated back and forth motion to thoroughly clean even the dirtiest areas. For smaller and more concentrated methods, Roomba's spot cleaning mode quickly gets rid of dirt and debris. The robot uses clip sensors to avoid stairs and drop-offs while cleaning. Roomba cleans when it's convenient for you. The robot can be scheduled to perform up to 700 when you're not home. Roomba is always charged and ready to clean. The robot automatically goes back to its home base to recharge between cleans. With Roomba's convenient remote control, you can turn the robot on and off, perform regular and spot cleaning, and steer the robot around the room. With Roomba, there's never any guesswork. When the dust bin is full, the robot turns on an indicator light to let you know that it needs to be empty. Roomba is so easy to use. The robot's intuitive touchpad interface eliminates mechanical buttons, letting you schedule and control the robot with just the touch of your fingertips. Roomba methodically and thoroughly cleans multiple rooms. Virtual wall lighthouses ensure the robot fully clean the entire floor in one room before letting it move into the next room. The iRobot Roomba vacuum cleaning robot cleans your carpets and floors on its own, so you don't have to. Just press the clean button and let the robot do the dirty work.
Now coming to the state-of-the-art technology in SLAM, there's a lot of, in these days, technology moves very fast, and you won't even know that you have a new method to, resolve a certain or your new approach to a given problem before it even, comes into the market. So there's a lot of advancements that are going on in this regard, but we'll talk very briefly about three methods that I thought were really interesting. So one of which, okay, let's start with the extended Kalman filter. Okay, so I was already talking about the Kalman filter earlier, but the Kalman filter is nothing but it defines the system in a mathematical model, and then you use the sensor information to correct yourself and generate a good mathematical model of the system, and then use the sensor input to localize and map the system based on this information, right? So extended Kalman filter is nothing but it also enables us to generate the same model and also map and localize, even though there is nonlinearity present in the system, right? So any given real system is a nonlinear system in general. How good you are able to linearize the system and how good you are able to use the system to generate a good model out of it. That's what the extended Kalman is the goal at the end of the day. So extended Kalman filter is nothing but it's an extension of the Kalman filter with the ability to deal with nonlinear characteristics that are generally expected in any real world system. So that's a very high level detail about that. Now coming to RATSLAM is nothing but it's a method that is based on the hippocampal model of a rat. There's a lot of research that is happening today based on the neural networks and all of these different new methods that are coming into play today. So this one, RATSLAM, is nothing but its system model itself is based on how the rats are able to perceive the system and place themselves in a given system, and all of these different information and how it is perceiving the information and how it is processing information. So that model is being used to develop an algorithm to do that. Now coming to the local bundle adjustment, this is a visual method. It uses visual method to generate the model of the environment. So basically, it basically creates the 3D point clouds and defines the scene that is coming in from the sensor, which is a camera, and then it will try to put yourself on the environment based on this information. So I'll keep this part at a very high level because it's pretty advanced topics, and we'll talk about them once we start with the course. Going to the next one. Okay, evolution of SLAM methods. As you know, autonomous vehicles is the booming industry at this time, and right now there is a lot of need for autonomous development engineers and in autonomous space, wherein you have a lot of opportunity in this space. So at this point, where the industry is at, we are mostly focused on developing level 2 and level 3 autonomous systems. I myself work as an autonomous vehicle engineer. So currently, the industry is primarily focused on level 2 and development of level 2 and level 3 autonomous features. The bottom left picture will give you a general idea of what is the different levels of automation and where we are at with it at this point. So level 2, level 3 autonomous features are basically, partially human. The human is ultimately responsible for it, but the system gives you the ability to automate the driving and all of these different aspects. But not all aspects are automated. The user is still responsible for any outcomes of anything that comes out of using these technologies. So in these different levels of autonomy, as I said, localization and mapping are always one of the major components of any given autonomous systems, because that is the heart of the problem, right? Because if you don't know where you are at, if you don't know your environment, then there is no autonomous system. So SLAM technologies are always going to be the heart of the problem. So developing strategies to developing strategies to automatically perceive the system and also use the information to localize and all of these different functions, that has become a challenge. And the SLAM technologies, or the SLAM methods, are improving on a very high pace, and they're playing a very big role in terms of enabling us to get these new technologies. Okay. So the other thing that I will just talk about very quickly is about the connected features. Connected features are nothing but like your phone. Your phone is connected to the network. Similarly, your car is connected to the network, and then you have network to vehicle communication and vehicle to vehicle communication. You can have a number of different combinations to it, and you use information from all these different devices, and it will help you put yourself on the map, and that's a very high level introduction to the connected features as well. So that is also one of the major areas where SLAM comes in, wherein SLAM will read the environment. You have 100 cars going on a road, then you have all these different cars that are collecting information using the sensors that the car has, and then all the sensor information is collected, and then it's put on a certain cloud or somewhere else. Then this information is used by something else, which is a different car, and it's used to localize itself and or better its localization function and localize itself better on the map. So things like this. So these connected features are also helping us improve upon these different technologies that we're having right now. Okay, let's talk about very briefly about the career paths that you have. Think of anything, any system, whether it's cars, whether it's farming, whether it's airplane, or whether it's underwater vehicles, or whether it's a factory environment or a home environment. You can take any example, and you will always find one example for a robotic system. So the opportunities of being in this space are endless. I mean, I just don't have enough space here to give you all the examples of all these different fields that you can be in for any for the robot for being being a robotic engineer. So I've given a few examples. Autonomous cars is, as I said, it's a booming industry at this time, and a lot of countries are passing regulations to move to driver engineless cars like electric cars and all that. And along with electric cars, autonomous vehicles, autonomous features are also becoming a norm in the autonomous vehicle industry, or the vehicle industry in general. So that's one example. And then the defense industry, of course, you have your drones, your fighter aircraft that is having more awareness by themselves, and then you have your submarines, underwater unmanned vehicles, all of these different stuff. It's interesting, and all of these different stuff use autonomous systems. And of course, the factory robots. A lot of factory automation is coming in these days, wherein a lot of work that is being done by people these days is moving on to be done by the robots, which means that they need to be able to, perceive the system or perceive the environment. Of course, that's by default for any given robot. So factory robotics, that's one area where you have a lot of opportunities. And of course, commercial airlines, that's one of the other major areas. UAVs, for farming, for UAVs, for n number of applications. I mean, I'll leave it to your thought process to perceive that the mid nature of that opportunities available to you. And then farming is that field robotics. It can be pipeline inspection for any oil pipeline. You have drones that are being made to do that. And then farming, autonomous vehicles are being used on a very wide range these days, especially when it comes to farming. And then inspections of the pipelines, as I said already. A lot of these different applications also come into the field robotics.